Unless you just arrived back on Earth from planet Zog and been out of communication for decades due to a faulty telecom line, you'll be well aware there's a concerted effort to convert to green energy. Some of the elements required for this technology are in abundance in the marine environment. So this has brought marine mining from the out of sight, out of mind spectrum to the forefront of environmental concern. There are a variety of alternative energy techniques, each requiring specific elements. Some are the usual suspects, while others, such as cobalt, are relatively rare in terrestrial deposits compared to the abundance available in marine deposits. Now let's bring the elephant in the room to centre stage, or rather, given the marine environment, the whale to the centre of the pool. The title of the article from which this table is taken is central to those who will be investing in future green energies. It has to be profitable. In 2020, the World Bank produced a report in which it quantified the demand for essential elements in the future. These spread across the periodic table, although some occur together in polymetallic deposits, such as copper, nickel, iridium, copper, lead, zinc, silver, and copper, cobalt. The World Bank estimate of an increase in 7% in copper production seems rather underdone given copper's essential role. Instead, an alternative estimate is shown here, revealing that over 2 million tonnes will be required by 2050. Richard Harrington produced an important paper in 2021 summarising the research that his group at Imperial College London is undertaking on the demand that green energy will be making on future mineral industry. The figures for converting vehicles in the UK to EVs are sobering. It will require twice the current production of cobalt, 3/4 of the current world annual production of lithium, the entire world annual production of neodymium, and our old friend copper, over 2 million tonnes. And when those figures are extended worldwide, it is mind-blowing. This presents a compelling case for increasing in mining to secure a greener future, which is rather counterintuitive. This cross-section of an ocean basin shows us the major features. All ocean basins have mid-ocean ridges with a mantle upwelling below it. The deep mining deposits consist of 3 types. There are hydrothermal vents on the mid-ocean ridges which host polymetallic sulfide deposits rich in zinc, lead and copper at depths of 500 meters to 5 kilometers. Seawater circulating through fractures dissolves metals from the surrounding rocks, then mixes with cold water and precipitates metal sulfide minerals. At depths of over 4 kilometers depth, there are polymetallic nodules rich in iron, manganese, copper and cobalt found on the surface of or partially buried in the sediment. These have been precipitated from the seawater through what is possibly the slowest chemical reaction on Earth. Where seamounts or ridges exist, ferromanganese crusts rich in cobalt and nickel develop at depths of 800 meters to 2.5 kilometers on the exposed rocks by precipitation from seawater. 2 other types of marine deposits occur. Phosphate deposits are found near or on submerged continental crust, while placer deposits on the continental shelf are derived from material transported from the adjacent terrestrial environment. These 2 types of deposits will be discussed in 2 presentations later in this session. The restriction of active hydrothermal vents to plate boundaries hides the fact that inactive vents and their sulfide deposits are carried away from mid-ocean ridges during seafloor spreading. Therefore, all oceanic crust potentially has such deposits hidden beneath the sediment layer. 3 places will be discussed: the Clarion-Clipperton Zone, Solwara 1, and Discol. This map shows the exclusive economic zones, as well as an exclusive zone around Antarctica in the oceans. Interestingly, there's a Chinese publication that shows the same map, but with those exclusive economic zones omitted. The Clarion-Clipperton Zone, which stretches from Mexico to Hawaii, is approximately the size of India. but it contains 4.5 times the worldwide terrestrial reserve of manganese, nearly 3 times that of nickel, and over 7 times that of cobalt. So it's rather clear why it is of economic interest. An important issue with marine mining is exactly who owns the seabed. So in 1982, the UN decided the seabed outside exclusive economic zones is the common heritage of mankind. It set up the UN Law of the Sea Treaty. The US did not ratify this, so may not participate in marine mining in international waters. It also set up the International Seabed Authority, which issues permits for exploration and mining. China's top of the table, and most permits have been issued for nodule mining in the Clarion-Clipperton zone. It's been rather slow in developing a code to regulating mining, so this has prompted one of the main member states, Nauru, to trigger a subclause in June 2021 that will allow the company to commence mining its licenses in the Clarion-Clipperton zone within 2 years, regardless of whether a zone has been produced. So Nauru has this and this as their 2 licenses, and this map shows that this area is rather like the League of Underwater Nations. So if they trigger the mining, then there's a potential for everybody to start mining in this area. Not unnaturally, this has caused great consternation amongst conservationists, resulting in a call for the moratorium on deep-sea mining. At the IUCN World Conservation Congress in September 21, 81 governments and government agencies, that's 64% attending, voted in favour of the moratorium, while 8 voted against and 28 abstained. 577 NGOs and civil society organisations, that's 90% of those that attended, also voted in favour, while only 32 voted against and 35 abstained. Interestingly, China seems to be proposing to coordinate with Germany, India and South Korea as regards developing deep-sea environmental management plans around southern Africa. With regards to how mining will take place and the effect on the ecological communities, polymetallic sulfide deposits involve quarrying the vents, and so the unique and important ecological communities around them will be destroyed. In 2007, Nautilus Minerals took over the Sawara mining project, and that is mining hydrothermal vents in the Bismarck Sea. The company went bust in 2019, and they've left the Papua New Guinea government deep in debt. But the one thing they did do in their operations is actually look at the potential impacts of this mining operation, with both local focus problems and international focus problems, most notably sediment plumes, which are going to affect other types of mining as well. Mining manganese nodules from abyssal plains is a major problem with regard to sediment plumes, because you get decollecting plumes from the collecting vehicle, as well as dewatering plumes from the vessel at the surface. This is obviously going to have a serious effect on filter feeders and sediment feeders that exist on the sea floor below. As for the cobalt-rich ferromanganese crusts on ridges, they will also require mechanical stripping, so there will be the same environmental issues as the polymetallic sulfide deposits. There have been studies on the impact of mining, some of which have been going for 30 years, notably at Discol in the Peru Basin, and they show there's negligible recovery of communities and the physical environment in those 30 years. So, conservationists will argue that most of the species and ecosystems in areas where mining would occur have not been well studied, nor have the potential consequences of mining to these and wider ocean systems. On the other hand, the people who are going to want to mine say, in our considered opinion, the impact of nodule mining will be magnitudes less than the equivalent impact of the mining on land for the volumes of metals that we will need in the future. So will the twain ever meet? Perhaps it's time to travel back to planet Zog.